So hello everyone, welcome to the part 3 of the coordination chemistry series, and today we are gonna mainly talk about the bonding segment. I guess you have been watching the part 1 and part 2 as well in our askIITians official YouTube channel. There you have noticed that in the part 1 we have been talking about the nomenclature segment, whereas in the part 2 we have been mainly focusing in the isomerism segment. After watching those two videos, guys, you can definitely start watching the video 3, because in this video we are actually gonna combine the part 1 and part 2 concepts as well, because you can clearly understand this is the last part of the chapter. So definitely whenever you are going down the chapter, they would use the previously taught topic, previously discussed topic in this final chapter, right? Final segment. So that is what's going to happen. So make sure you have revised the part 1 and part 2 first before you start watching it. In this video, guys, we are actually going to talk about one of the most important part of coordination chemistry, which I guess many of you are having issues with by now, right? That is the bonding segment. Like here, we are going to mainly talk about how to understand the strong field and the weak field ligands. Why are they strong field and weak field, which is not even written in the NCERT properly, which I'm going to explain to you. How suddenly we can consider these people as strong field, why these people are weak field. After that, guys, we are also going to talk about what is the synergistic effect, then the carbonyl molecular orbital diagram, then the magnetic character of coordination chemistry, followed by the color of coordination complexes. In there also, we are going to talk about what all types of transitions are there, which are responsible behind the color of the coordination complexes. Guys, we know about DD transition is there. Along with that, guys, there is LMCT and MLCT. Also, we are going to talk about all these three things here. Like I said in the very first video, our target would be keeping things in the boards level and max to max in the JEE means level, not in the JEE advanced level. So considering that, guys, whatever I will be teaching you in this video, you can refer to your NCERT and understand all those things. The things which would be taught in the classes would be containing the crystal field stabilization energy, the Jahn-Teller distortion, and a few more topics regarding the metal carbonyl complexes. Then we have organometallic complexes, ferrocene complexes, sandwich complexes. This is what we are going to talk about in the sessions only, all right? These are not the type of topics that we can expect to come in the school examinations for sure, guys, even not in JEE mails, right? After this, we're going to see some PYQs as well, whether we can solve them or not. And yeah, that is how we are going to plan today's session over here, okay? So make sure you watch it till the end. If you feel like there is some topic that you know already or you understand it, then guys, you feel free to skip that portion, all right? So let's get started with the topic here. I hope you have been understanding everything that I have taught you so far. There is something about this topic, guys, the one that we are going to take today. This part, although it is one of the most important segment of this chapter, still there is always a miscommunication or misconceptions going on in this segment. Okay, I'm gonna cater every single point over here, right? So when I was a student, I felt some of the problems when I learned coordination chemistry. Now, right now also, when I'm actually still, when we are going through the coordination compounds, coordination chemistry is something now. It is gonna be continued in your future classes as organometallic compounds, right? Beyond grade 12, if you move on with chemistry. And in there, guys, what actually happens is you get to know about a lot of things, which you are not being taught in grade 11th and 12th. And that creates a lot of confusion actually in your mind. So I'm going to refer to a few things from there also in order to make you understand about the topics in a proper manner, right? So I would be sometimes, guys, elevating the level of the sessions so that you can understand the topic better. Okay, it's not like you have to remember every single thing that I say here, but yes, it's always good if you know the things from where it is coming and like how many types of ligands are there, how are they showing the strong and the weak character. What is an octahedral complex? What is a tetrahedral complex? By nature, we know that what is an octahedral, what is a tetrahedral, but how are they, chemically combined in a way, and what kind of effects are they showing? What kind of stabilization or destabilization are they showing? What are the effects of octahedral geometry and tetrahedral geometry in the splitting? These are all the things that we are going to cover up in today's session. Okay. Now, let's get started. Keep the heading as bonding. Do share your views, guys, over the YouTube comment section as well. If you believe that these sessions are helping you, then also you make a comment on it. If you feel like you want to watch more of these kind of sessions, you want to watch me solve some JEE advanced question or JEE means question, and if you want the series of JEE means questions over the YouTube webinar only, then also guys we can make it happen. All right, so just make sure that whatever you feel like you put it in the comment section. We will definitely try to make that thing. Right, now coming to the point over here again, how the bonding works here in coordination compounds. Right, first of all guys, I believe that you have watched the first video where I have made it clear that how the coordinate covalent bond and the covalent bonds and the ionic bonds are different. When we talk about coordinate covalent bonding or coordination chemistry, here guys, you have a criteria that you have to fulfill. The criteria is pretty simple. You have to have a electronically rich substance, which is a donor, which will be acting like a donor, which we are calling as the ligands. Right. And there are electronically deficient substances as well. Electronically deficient substances as well. When we talk about the electronically deficient substances, guys, we are actually talking about the acceptors. We're talking about the acceptors. And in our syllabus, the acceptors are actually the D block metals. This much, I guess, we are all clear from our last few discussions. Now, the point is, when this bonding is happening, how is the bonding happening, guys? Let's say I'm giving you an example over here. Let's say I have ammonia. Ammonia has a lone pair. Okay. So far, the bonding that ammonia shares over here, guys, that is a covalent bonding, right? Now, when we are trying to talk about the coordinate covalent bonding, what actually happens is, let's say ammonia is treated with an acidic solution. Guys, you know that in the acidic solution, you have a lot of H+. H+ is a species with no such electrons present in it. As a result, H+ can be denoted as H+ with a box in it. Now the lone pair is being donated in there. Now guys, focus in this part with them. The donor donates both the electrons to the acceptor. An acceptor accepts both the electrons of the donor. So that means in order to make a coordinate covalent bond, you need excess electrons. One person with an excess electron and the other person with vacant orbital. This is something you have to understand first. You need another person with a vacant orbital. Without it having a vacant orbital, guys, you cannot make a coordinate covalent bonding. Why am I saying that? When you learned covalent bonding, guys, do you remember there? The criteria was you have to have unpaired electron present in your orbital. You remember that? So that means, let's say oxygen's valency is 2. How did you come to the conclusion? It was like oxygen, if you write down the electronic configuration, 1s2, 2s2, 2p4. So if you draw 2p4, there are 2 unpaired electrons. That means it can make 2 bonds. Correct? But in coordinate covalent chemistry, guys, it's not unpaired electron. You have to have vacant orbitals, vacant boxes. That is the number of bonds you can take. This is the first thing I want you to be 100% clear before we move forward with it. Okay? Now, have a look. How many types of complexes are you gonna see in this part, in this chapter? Okay. See, mainly we are gonna see, I told you in the second video as well, there are 2 types of coordination number that they actually take in here. One is 4 and the other one is 6. Okay. But that doesn't mean only these 2 are there. There can be 5 as well. There can be 3 as well. All these coordination number can also be there. Generally, guys, 4 and 6 is being discussed in the NCERT level. Okay. If you have, let's consider 5 as well. Let's say 4, 5 and 6. 5 is very rarely asked. In ferrocene complex, 5 is being asked. Whenever your coordination number is 4, guys, I told you in the last session as well, it can be tetrahedral or it can be square planar, right? These are the 2 things it can become. When it is 5, it can be trigonal bipyramidal, TBP. Right? This is what these things are coming from chemical bonding of grade 11 only. Right? 5 is TBP, 4 is tetrahedral. Whenever it is 6, guys, it would always be octahedral. Octahedral, I'll be abbreviating like this, O and an H. It would always be octahedral. Now, when we say it is tetrahedral, guys, tetrahedral hybridization is sp3. Square planar, I'm gonna make you understand about it, but right now you just note it down. Square planar hybridization is dsp2. How is it coming? How is the D coming from? Where is the D coming? That I'm gonna talk about in the bonding site. Okay. When we talk about octahedral, guys, there can be two types of hybridization there. One is sp3d2. This is, I guess, all of us are very much aware of. sp3d2 is octahedral. sp3d is trigonal bipyramidal. sp3d is trigonal bipyramidal, and sp3d2 is octahedral. And the other one that you can do is d2sp3. This is also octahedral. There can be two types of hybridization that can undergo octahedral geometry, sp3d2 or d2sp3. Again, I'm not explaining anything right now, guys. I'm just telling you the facts over here. Okay, two types of octahedral complexes can be there. Now, this sp3d2 people, whenever somebody has an sp3d2 hybridization, we call them outer orbital complex. Outer orbital complex. And whenever somebody has d2sp3, we call it inner orbital complex. Outer orbital complex and inner orbital. Okay. Now, let's try to understand this segment now. Okay. First, according to BBT, valence bond theory, in order to form coordinate bonding, we need to have vacant orbital of the metal. So central metal atom has to have a vacant orbital there in order to have a coordination bonding. Okay. Now let's jump into this fact now. Let's say they have given you this molecule FeH2O whole 6 3. Okay, quickly guys, pause the video and try to name the complex on your own first. The naming of the complex I have taught you in the very first video. I guess you remember from there. So you quickly pause the video and try to name the compound. Okay, I guess all of you have tried it once. So here's the name: hexa-aqua iron 3. Always write the oxidation number of iron in a quote bracket, right? Hexa-aqua iron 3. If it was anionic, guys, it was hexa-aqua ferrate. If it was anionic, right, it is cationic, so iron. Now this is a complex. They would ask you, what is the hybridization of this? They would ask you, what is the hybridization? When they ask you what is the hybridization, always remember, guys, they ask you the hybridization of the central metal atom. Always. Now, when they ask you this question, what you're gonna do is, you're gonna think about bonding the systems, then drawing the diagram and stuff like that. But let me tell you how to do this. Guys, in order to get the hybridization, there's a very simple method. What's the simple method here? You see, there are 6 ligands associated with the iron here. If there are 6 ligands, then the coordination number is 6 here. So either your answer is gonna be sp3d2 or d2sp3. First, get this thing clear in your mind. You cannot have any other hybridization over here, guys. It has to be either sp3d2 or d2sp3. This must be understood. Now, which one would it be? For that, right now I'm gonna show you a bigger method, a method that you'd be doing in your school examination. Alongside, I'm gonna give you a shortcut as well, like always. Okay. First, what you do is you write down the electronic configuration of Fe3+. Why Fe3+? Because, guys, you can see that iron, if it is considered as X, water is 0. So overall oxidation state of iron over here is +3 only. That's why Fe+3. Iron is 26, so I guess you can draw the electronic configuration. Argon 18. It is 26, so write 3d6 4s2. If it is 26, write 62. See, 62. 6 and 2. Just write like that. You have written that. But it is, guys, 26, but it is 3 plus we are talking about. This is iron's electronic configuration. So when it is 3 plus, that means 2 electrons from here, 1 electron from here are gone. This is your iron 3 plus electronic configuration. Now, once you're done with drawing the electronic configuration, here comes the next one. Now, guys, as usual, draw the orbitals. 3d5. The orbital has 5 boxes, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. 4s orbital has nothing in it. Guys, if there is the principal quantum number is coming as 4, if it is 4s, then guys, definitely we have 4p, definitely we have 4d, definitely we have 4f, right? So let's draw them as one. This is 4s. This is 4p. This is 4d. I could have drawn 4f, but that is not needed. I'm going to show you why is it not needed. Now, guys, you tell me one thing. If I have to draw FeH2O whole 6 3 plus, if I have to draw this die, then there are 6 water molecules I have to make the bonding with. I have to make 6 water molecules bond with the iron molecule of mine to make coordination come. Correct? This is my iron's electronic configuration. So I'm going to put the water now. So where should I put? Now here's the part. If it was our covalent compound, then I would have been putting the water here, unpaired electron. But guys, it is not our covalent system, it is coordinate covalent system. For that, what did I tell you? We need what? We need vacant orbital. Save it with me. So we need vacant orbital here. So as a result, we need 6 vacant orbital for 6 water molecules. We need 6 vacant orbitals for 6 water molecules. Okay, note it down real quick now. Okay, I hope you guys are all done with this. Now the point is over here, guys, after you have drawn all these things up, now here's the question, like what would be the hybridization? For hybridization, guys, you know that all the orbitals that has been taking part in sigma bonding formation in the coordination bonding, we are going to take them in only under consideration. Here, if you see, we are using s orbital, 3 of the p orbitals and 2 of the d orbitals. So guys, the final answer is sp3d2. So if you remember, we talked about this. It is either going to be sp3d2 or it is going to be d2sp3, correct? So it is coming as sp3 here. We are clear? All right, guys, it is sp3d2. How many unpaired electrons are there over here? 1, 2, 3, 4, 5. This I would be needing during the magnetic moment discussion. Right now, let's just note the number of unpaired electrons we had. Okay, they are all in 3d orbit. So guys, how is the molecule gonna look like? So let me draw it in the right hand side of this. So whatever it is, sp3d2 or d2sp3, guys, you know that whenever the coordination number is 6, it is gonna be an octahedral complex. So this would be my iron. 1 up, 1 below, 1 right, down, left, down. H2O, 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 H2O. This is your structure of FeH2O whole 6 plus overall plus 3 charge. That's it, guys. Simple, isn't it? It's a very simple thing, guys. It's very, very important, but very simple actually. Let's go for the next one. Now, this question, guys, you'd be pausing the video and you'd be trying to do it on your own, okay? The compound that is there is FeF6, 3 minus. Okay, try it out, guys. Before we solve this question, you can see that again the coordination number over here for the iron molecule, for iron, the coordination number is given as 6. That means, guys, on the very beginning, you can say it is either gonna be sp3d2 or it is gonna be d2sp3. Correct? So now figure it out. Pause the video and figure it out. Okay, I hope all of you have tried this question once. Now, guys, first what you have to do is, first we have to find out the oxidation number of iron over here. So guys, take it as x. Now x minus 6. Why minus 6? Because every fluorine is minus 1. So total x minus 6 equals to minus 3. So x is coming as plus 3. Guys, this is the first step. Finding out the primary valency of the central metal atom is the first problem for you. Okay. Then the second step is, it is again Fe3 plus, guys. So Fe3 plus, we have just done it a minute ago. It is argon 18 3d5, correct? That means 1 2 3 4. 1 2 3 5. This is 4s. This. Okay. Now here also again, guys, you have to put 6 fluorine atoms over here, but you cannot put it in the unpaired segments like covalent bonding. You have to put it in the vacant orbitals. So now if you start putting them in the vacant orbitals, then guys, how would it look like? One F minus would come, it would donate both the electrons. Second F minus would come, it would donate both the electrons. Third, fourth, fifth, sixth. Total 6 fluorines are there. So I'll be putting 6 electrons in 6 orbitals. Which all orbitals are we using, guys? 4s, 4p, 4d. So what is the hybridization then? Again sp3d. Understood? Now let's go for the next question. With this method, guys, if you try to solve, how would the molecule look like? Same way. F minus, F minus, F minus. That's the compound. FeF6. Okay. Now guys, what we do is we'll solve another question, which is CO NH3 whole 6 3 plus. Come on, solve this question on your own, then we would see. Pause the video, guys, give it a try. Okay. Now here also, first you find out the oxidation number of cobalt over here, guys. Cobalt's oxidation number is ammonia is 0, so cobalt's oxidation number is plus 3 here. Cobalt is 27th element, so that means cobalt would be argon 18 3d7 4s2. So guys, that's a shortcut. If it is 27, you write 72. Write 3d and 4s and then write 72 on the top of it. Okay. Now 3 electrons are gone. If I'm making CO3 plus, that means 3 electrons are gone. So 2 from here, 1 from here, 3d6, 4s0. Now start filling the electrons. Guys, by now you have understood that 3d orbital, as they are filled partially or fully, whatever the situation is, as they are filled, there will be no electrons going inside them. So we'd be starting to fill from 4s orbital. So 4s, 4p and 4d. So what is the answer coming then? Guys, over here there is 1 ammonia, 2 ammonia, 3 ammonia, 4 ammonia, 5 ammonia, 6 ammonia. Because you have 6 ammonia molecules, you have 6 sigma bonds getting formed by the 6 ammonia, and guys, your final hybridization is again sp3p. Which orbitals are there? 4s, this is 4p, this is 4p. Okay, so far guys, I guess we have understood every single thing in here. Now I'm gonna move on to the next part. This is the move overall. This is how the bonding works in valence bond theory. But guys, there has been some modification in the bonding segment now. Now, what was the modification? Let's say I had a question, I had a compound which has been given as Fe CO whole 6 3 plus. Let's say this question has been given to you. Let me think once, guys. Let's say this question has been given to you. Then how would you answer the question here? Again, guys, you would be thinking it can be sp3d2 and it can be d2sp3. Correct? Now you go again with Fe3 plus configuration, right? Oxidation number of X is gonna come as +3. You go again with Fe3 plus configuration, which is gonna be argon 18, 3d5, 4s0. Now guys, 3d orbital is not accessible because there are electrons in there. So I have to start filling the electrons up from 4s. So 4s, 4p and 4d. In these 3 orbitals, we have to start filling the electrons. Now guys, now you apply some common sense over here. If I start from s orbital, then definitely this one would be my answer, sp3d2. S, 3p orbital, 2d. So sp3d2 should be your answer. But that is not the right answer. The right answer is d2s. Now why is that? Why is it d2s? How did it become d2sp3? So for that guys, they give you a lot of different kinds of logic. But what I'm gonna tell you right now here, that is the most authentic logic, all right, about this thing, which is definitely guys, which is written in the NCERT, as well as from the book that I'm teaching you from is, it's called the Crabtree. Crabtree is a particular book for inorganic chemistry that is being used in masters. Okay, so my entire topic, whatever I'm teaching you guys, it is coming from the I am taking the contents from the book Crabtree for us. Okay, now anyway, let's come to the real reason behind this D2sp3 configuration. First, let me show you how is the D2sp3 configuration come. So what they do first is they draw the molecule like this. 1, 2, 3, 4, 5. 4s, 2p, 4p. Okay. Now what happens is they are saying it has been seen that it is coming as D2sp3. Now they are trying to give you the logic like, okay, you know what actually happens over here is these two electrons, they pairs up. They pairs up. If they pair up, then what would happen? 1, 2, 3, 4, 5. This is my 4s, this is my 3d, my 4p, my 4d. Now see, if I start filling the electrons up for carbonyl system, 1, 2, 3, 4, 5, 6. But the question comes like, why pairing? Why am I pairing them? That's the question, right? Now, if you notice guys, the number of unpaired electron in this compound is only 1. This compound is called inner orbital complex that I told you before as well. sp3d2 is called outer orbital, d2sp3 is called inner orbital complex. Now when I call it an inner orbital complex, you can understand why is it inner orbital complex. Because guys, when I'm writing sp3d2, check your copy once, this d orbital is actually a 4d orbital. But in this D2sp3 configuration, the d orbital is actually a 3d orbital. So in one case, I'm using outer d orbital, that's why it is outer orbital complex. In the other case, I'm using inner d orbital, that's why it is a inner orbital complex. Is that clear so far? Now have a look. Now, why is the pairing happening over here? So guys, now you give the heading as crystal field theory. Crystal field theory. Okay. Now, what is this crystal field theory over here? First, you note like this. Whenever a metal is approached, by the ligands. Whenever a metal is approached by the ligands, they gets into a ligand field and shows distortion from degeneracy. Distortion from degeneracy of orbitals. Very, very important concept, guys, over here. Whenever a metal is approached by the ligands, they gets into a ligand field and shows distortion from degeneracy of the orbital. What do I mean by that? What is the degeneracy statement? What do I mean by that? Degeneracy means whenever you draw the orbitals, like let's say I'm drawing the d orbitals, right? So when I draw the d orbitals, you have always noticed that we draw it in this way. You know what does that mean actually? That means like if I put it against the potential energy curve, all the d orbitals that we have, what are the name of the d orbitals? dxy, dyz, dzx, dx square y square, dz square. All the 5 d orbitals have same energy or similar energy. So degeneracy means, guys, same energy. If I ask you, what is the degeneracy of the d orbitals? The answer is going to be 5. It is a penta-degenerate system. Okay? Because there are 5 orbitals in the same energy. It's like that. Clear so far? Now, they are saying that it shows a distortion from the degeneracy. That means this degeneracy gets distorted. Right? This distortion is something like in energy base, guys. This distortion is based on energy. Now, hear me out properly. What do I mean by this segment? This is a very, very important segment, guys. So have a look. First, let's write the definition of octahedral complex. Okay. Now, in this part, guys, make sure that if you are watching this video in a high speed mode, guys, in 2x speed or something, make sure you slow down now, because I want you to sink this entire topic in when I teach you this. Okay, this is the most complicated part of this chapter. Now, what is an octahedral complex? Now you write like this: according to crystal field theory. According to crystal field theory, guys, see, there are many theories in coordination complexes. First, valence bond theory, then valence shell electron pair repulsion theory, then from there, guys, crystal field theory, then adjusted crystal field theory, then molecular orbital theory. All these theories are there. We don't go into much of more details in the ACFT, adjusted crystal field theory, or anything, and the molecular orbital theory also not being taught in that detailed manner. Okay, only crystal field theory is the only important part of this part. So according to the CFT, an octahedral complex is formed. An octahedral complex is formed when the ligands approach the metal along the axis. Okay. According to the crystal field theory, guys, what is an octahedral complex? Octahedral complex is whenever the ligands are approaching the metal through the axis. That is called octahedral complex. What do I mean by this entire part now? Have a look. Okay. Guys, I believe that you know that it is dxy, dyz, dzx, dx square, y square, dz square. These orbitals, how do they look like? First, you need to know that. Okay. Let's say I'm going to draw some structures for you. Just one second. Okay, have a look now. When I say dxy, that means, guys, I'm talking about x and y orbit. Dxy is a, d orbitals are double dumbbell, and when the double dumbbell character is along the plane, we call it dxy. So this is planar geometry. This orbital is planar. dxy is along the plane. There are two types of orbitals that we have for d orbitals. Two types of them. One is planar, another one is axial. I'm going to show you this. dxy. What is dyz, guys? Let's say this is y and this is z axis. Then in between the y axis and the z axis, if I draw the double dumbbell shape, that thing is going to be called as dyz. Similarly, guys, what is dxz? If this is x, this is z, then dxz would be along the x and the z axis. Right, these are the three orbitals. What are the two other things, guys? dx square, y square, dz square, right? Now, I want you to notice one thing over here. dxy, dyz, and dxz, all three of them are along the planes. They are not along the axis, they are along the plane. Now, guys, I'm going to draw the axial orbitals for you. Axial orbitals are dx square, y square, and dz square. Let me draw it in the right hand side. So, how is dx square, y square gonna look like? We always have to keep double dumbbells over here. Now see, this is x-axis, this is y-axis. Now see, it is not in the plane, it is along the axis. So dx square, y square is an axial orbital along the axis. And the last one over here is dz square. This is along the z-axis. This is also an axial orbital. So, guys, in the 5 d orbitals that we know about, there are 3 of them are axial, 3 of them are planar, equatorial or planar, and 2 of them are axial. Right, this much we are all clear. Now have a look. What is this crystal field theory saying? How are the ligands approaching for crystal field theory? According to the crystal field theory, octahedral geometry, for octahedral geometry, the ligands are approaching. Come on, ligands are approaching along the axis. Along the axis. Now here, guys, look at me. The ligands are approaching along the axis. Fine. If the ligands are approaching along the axis, the ligands are electronically rich. And they would meet which orbitals then? They would meet the axial orbitals. Electronically rich ligands meet axial orbitals. What are the axial orbitals, guys? Axial orbitals are dx square, y square, and dz square. Now here's the thing. If they meet the axial orbitals, what would happen? The ligands are approaching with electrons. The axial orbitals also have electrons. So there will be an inter-electronic repulsion working there. Very common sense, right? D orbital also have electrons. The ligands are approaching with electrons. So there would be a inter-electronic repulsion working in that place, guys. If there is an inter-electronic repulsion works in that place, then there would be a repulsion, right? That repulsion, that interaction, what would happen there? There would be inter-electronic repulsion. There would be an inter-electronic repulsion getting formed. There would be a repulsion there. Due to this inter-electronic repulsion, what would I see is, we would see destabilization of orbital. We would see destabilization of orbital. We would see destabilization of the orbital. Which orbitals? These two orbitals. Why? Because the ligands approach. How? Along the axis. So as the ligands are approaching along the axis, they are coming with electrons. So the orbitals also have electrons. So the axial orbitals would get destabilized. Destabilization of orbitals. Okay. So now, so much we are clear, I guess. Achha, destabilization of which orbitals? We should write that, guys. Destabilization of axial orbitals. Destabilization of axial orbital. If there is a destabilization of axial orbitals, what would happen to the equatorial orbital now, the planar orbital? Now see, there would be an increase in energy due to the destabilization. So as the axial orbitals are getting destabilized, how would you show this, guys? How are they getting destabilized? By increasing their energy, they are getting destabilized. In order to keep the law of conservation of mass intact, in order to keep the law of conservation of mass intact, what would happen? The planar orbitals, guys, very, very important this part. The planar orbitals would get stabilized. Very, very important. Axial orbitals getting destabilized, the planar orbital getting stabilized. So why is that happening? See now. Let me draw this. It would be much more clearer to you. See now. These were the 5 d orbitals in the degenerate state. Okay, these are the 5 d orbitals. But what actually happened is, guys, like I said, when the ligands, when they approached the system, what happened is, as they're approaching along the axis for octahedral situation, as they're approaching along the axis, the 2 of the axial orbitals gets destabilized. Destabilization means, guys, increase in energy. They get destabilized. Now, in order to keep the total energy conserved, there's a law of conservation of energy. You remember, you cannot create or destroy energies, right? So if the 2 orbitals, which are the 2 orbitals, the axial ones, ax square, y square, and dz square, as they are getting destabilized, so somebody has to get stabilized in order to keep the total energy constant. So in order to do that, the dxy, dyz, and dzx, they get stabilized. Okay. This particular phenomenon that you just saw, This is called crystal field splitting. It's called crystal field splitting. What happens over here, guys? With respect to the center, energy center, we call it barycenter. We call it barycenter, the original energy. The 5 orbitals gets splitted into 3 and 2, and the overall splitting is denoted with delta O. Delta means splitting, guys. O stands for octahedral. Okay. The above orbitals get destabilized by, it has been calculated, they get destabilized by 0.6 delta O, and the orbital down below, they get stabilized by minus 0.4 delta O. Now, how do I know that? It's a very simple thing, guys. See, each orbital getting stabilized by 0.6 delta O, so 2 orbitals would be total getting destabilized by 1.2 delta O, and each orbital is getting stabilized by 0.4, so 3 of them would be destabilized by 1.2 delta. I told you, overall energy has to conserve, right? So the overall energy, the amount by which it got destabilized, that is the same amount the 3 orbitals would get stabilized, right? So that's why, guys, the above one is 3.6 delta O and the below one is 0.4 delta. That's how we write it. Okay. So this is called crystal field splitting of orbitals of the other. Now, according to group theory, guys, we call them T2G, and the above ones we call them EG. Here, E means doublet or doubly degenerate. Guys, I guess you understand what do I mean by degenerate. Doubly degenerate means 2 orbitals with same energy. And T2 stands for triply degenerate. What is this terminology G standing here for? See, G means gerade, U means ungerade, which is nothing but synonym of symmetrical and unsymmetrical. Okay, so these standing for only symmetrical and unsymmetrical, only for that. So guys, we call them T2G and EG to keep it short. So this is your crystal field splitting theory. So far we are all clear, guys. So how does the splitting happen and all? So long story short again, if you have the ligands approaching from the axial orbitals, axial sides, that is when only it is getting octahedral. Now see, this is also very much understandable. You don't have to mug it up or something. It is also understandable if you just do this. Let me show you. See, you are talking about octahedral geometry. So octahedral geometry means, guys, you can understand there will be 6 positions. See, if I want an octahedral geometry, I needed 6 positions. See, 1, 2, 3, 4, 5, 6. Here is the method, right? So you can understand, guys, in the octahedral geometry, they are approaching from the axial orbitals. As they are approaching from the axial sides, so the axial orbitals get destabilized, the equatorial orbitals get stabilized to keep that overall energy constant. That is called crystal field splitting. I guess we all understood this part, right? Now here goes the story. Give the heading as strong field and weak field ligands. What are they? Okay. Strong field ligands are the ligands, those who are high electron donor. And weak field ligands are the ligands, those who are low electron donor. Okay, that is how we understand what is the strong field. There is a series called spectrochemical series, guys. There is a series called spectrochemical series. According to that series, if you write the elements present in that series, I minus, SCN minus, CL minus, SQ minus, just 1 second, F minus, OH minus, water, ammonia, polydentate ligands, CO, NO, CL. Okay, this is the spectrochemical series. But you don't have to remember the entire series. There is a thing that you can do about this one. See, till water, everybody is weak field ligands. Water is a borderline ligand. So it is in between weak and strong. Now from water onwards, everybody is strong. Everybody is a strong field ligand. Now, how do we understand that what makes them strong field, what makes them weak? That part, guys, yet to come. So polydentate ligand, carbonyl, nitrosyl, and cyanide are considered as polydentate, are strong ligands, as strong field ligand, and rest all of them are weak field ligand. That's how you can consider. Okay. For ammonia, guys, if you are talking about the first D block cell, you know 3D, 4D, and 5D, 3 orbitals are there, right? Scandium to zinc is 3D series, right? And what is 4D series? Yttrium to cadmium is 4D series. What is 5D series? Lanthanum to mercury. Okay. Under the 3D series, from SC to Zn, for all of these people, when they are in +3 state, in that situation, guys, ammonia acts like a strong ligand. Ammonia acts like a strong ligand when they are in the +3 state. If they are in the +2 state, then this ammonia only, it acts like a weak ligand. But this particular information that I'm giving you guys over here, these are all for JEE mains and above level. Here, according to NCERT, they consider ammonia as a strong field ligand only. And if you notice, you'll always see that they are giving ammonia with a +3 complex only all the time. Always. Okay. That is in their syllabus, guys. So in your syllabus, so you don't have to worry more than this. Okay. Now, the point over here is, so ammonia is considered as strong field in this chapter so far. This part I'd be teaching you in detail, like when is it strong, when is it. There's another thing, guys, you need to notice. You need to know this field, the strong field, weak field, all these ligands based things, these are only applicable for 3D series elements. For scandium to zinc, for them only it is applicable. For 4D, 5D, every ligand is strong field. Let's note it down. Every ligand is strong field for 4D and 5D. For 4D and 5D series, every ligand is strong field. Why is that, guys? When you go to 4D and 5D series, your D electron increases, your F electron increases. That means DNF contraction starts coming in. Because of the DNF contraction, guys, your 4D and 5D elements are very, very polarizing power. They have a high polarizing power. The Z stars are very, very high. So whichever ligand is there, they make them act like a strong field ligand. That means, guys, they take a lot of electron from the ligands. And whenever you give a lot of electron to the metal, that means you're a strong field ligand. So guys, even if you don't even want, still they are like the Busuli Bhai or something like that. They would take a lot of money from you, okay, whether you have it or not, right? Similarly, they would take a lot of electrons from the ligand. So this strong field ligand and weak field ligand, this concept is only applicable for 3D elements. 3D series means, guys, scandium to zinc. Only for them this is applicable. For 4D and 5D, everybody is strong. Okay. Now, what would happen if you have a strong field ligand? What would happen if you have a weak field? Now you go like effect of field strength. Effect of field strength. Now have a look. Let's say I have 5D orbit, and they're making coordination number 6. That means octahedral complexes, and this is the scenario for weak field ligands, guys. The 5D orbital, they got splitted because the ligands are approaching. But the splitting won't be high enough because the ligands are approaching with low amount of electrons. Weak field means, guys, they donate low electron. Strong field means they donate a lot of it, right? That is how we classify them. So that the splitting is also so low. Whereas when I draw a strong field ligand, in that case, guys, what can we take? Say so when you have a strong field ligand, guys, what actually happens is it's a high split. There's a high splitting. Now, because of this high splitting, so for strong field ligand, guys, the splitting is high. Why? Because strong field ligands, they come with a huge amount of electrons. So when they meet the d orbital, they show a huge destabilization. Because they show a huge destabilization in d orbital, so there is a huge stabilization in d orbital as well. So like dx square y square and dz square. They get destabilized by a huge amount. So as a result, T2G has to get stabilized by a huge amount, and as a result, the gap between T2G and EG is increasing significantly, right? Now here's the thing, guys. That's the main part. Let's say I had 5 electrons in the d orbital, right? Remember, guys, they paired up for carbonyl complexes. They paired up, right? We were trying to figure out why did they pair up, right? And this is the verge where we are going to find that out. See, I have 5 electrons. Now let's start putting them in the electronic configuration. So 1, 2, 3, according to Pauli's exclusion, we have to put 1, 1, 1. Then after that, guys, where should we write the 4th electron? Here's the point. Should I write the 4th electron here, pairing up, or should I write the 4th electron here? The point is, as the splitting is not high enough, we can put it above here. Why is that? Because see, if you don't put it here, if you put it here, then what would happen? Then there is no jump that you have to make. But guys, in between these 2 electrons, there will be an inter-electronic repulsion working, which is also known as the pairing energy. So guys, what we say is, for the low splitting complexes, if you want to pair them, for that the energy that you need, that is really high. Let's say pairing energy is 100 joules. But rather than that, if I split it, if I make the jump, then it might be going to 50 joules or something. So that means, guys, for weak field ligand, the pairing energy is more than the jump. The pairing energy is more than the jump. So that's why the electrons love to make the jump instead. Is that clear? So the electrons, they make the jump. Why? Because to pair them up, they will take more energy. They need more energy. Rather than that, they make the jump. So 1, 2, 3, 4, 5. But when you are dealing with a strong field complex, here guys, you 1, 2, 3, but to make the fourth electron jump over here, you need a huge amount of energy because the splitting is very, very high. So here guys, the splitting is very, very higher than pairing energy. As a result, what you do is you start pairing them up. And that's why guys, under the presence of strong field ligand, we see pairing happening. One more time. When we are being approached by a weak field ligand, then the splitting is less. If the splitting is less, the electrons feel that they can make the jump rather than pairing, because the jump takes lesser energy than the pairing. But instead, if you have a strong field ligand, then the jump would be so high that they would feel like, okay, let's go and pair up. That's even better. Maybe here the jump is asking for 200 joules of energy, whereas the pairing is asking for 100 joules of energy. So they go for pairing up. Understood? As a result, guys, we come to the conclusion that for the strong field ligand, we see pairing. For the weak field ligand, we don't see any pairing. That's why when we have a weak field ligand complex, we call them high spin complex. Why high spin complex? Because there is no spin pairing. Whereas whenever we see a weak field ligand, there we call a strong field ligand, we call them low spin complex. So now guys, coming back to the question where we started all the steps. If you notice, when I gave you the question, this one, you can understand this is my strong field ligand. If this is my strong field ligand, then should I put the 5 electrons in the d orbital like 1, 1, 1, 1, 1? No, no. I should have been putting them, as it is a high spin strong field ligand. That means guys, the delta O is greater than pairing. As a result, what would you do? You would start pairing up. So that's why when you have been pulling the electrons, you went like 1, 2. First you went like this, 1, 2, 3. Should I put 4 and 5 here? No, because these two orbitals are higher in energy. So we should put 4 and 5 from the beginning again. 4. They would go for pairing. And because they go for pairing, guys, they vacate the internal d orbitals. As a result, guys, you get d2sp3 configuration. Okay, this is the entire theory here. Let's solve one question of this type. That's how they had given CO NH3 whole 6 2 plus. Now, when you go for, 3 plus. Wait a second. Let's go for 3 plus. So guys, that means CO is in +3 oxidation state, that is 27. So argon 18, 3d6, correct? So if you write 3d6, how should you write it? Okay, notice now. Ammonia is a strong field ligand according to this discussion of ours. So as a result, 1, 2, 3, 4. Now, as a result, the 6 electrons that is there, this is how I'm going to put them. 1, 2, 3. See now. Do it in a rough. 1, 2, 3, 4, 5. 1, 2, 3. After that, where should the 4th electron go, guys? Should it go up here? The answer is no. It's a strong field ligand. So the splitting is very, very high. So as a result, 4, 5, 6. 4, 5, 6. This is your 3D. Then you write 4s. Then you write 4. 4s would be having 1 orbital and 4p would be having 3 orbitals. So guys, the electronic configuration would be D2 S P, okay, sorry, 3 to 5 for a second, next 6 now, 3 4 5 DSP this is 4s orbital now, SP3. That's why we get, guys, D2sp3. So whenever are we gonna get D2sp3? Whenever the ligand is strong field ligand. Weak field ligand sp3d2, strong field ligand D2sp3. Okay. Okay, guys, I hope you have understood so far here how the bonding happened and how did we actually, the pairing and the non-pairing thing is working, right? So let's give it a go. Let's try a question over here. So the question over here is, guys, which you'll be solving, that is, let's say you have NiCl4, NiCl4, 2 minus, and NiCN4. You have to find out the hybridization in both the cases, guys. Okay. Now, first of all, how can we eliminate the rest of the part here? See, coordination number in both the cases is coming as 4. So it's either it is gonna be tetrahedral or it is gonna be square planar. For tetrahedral, guys, what is the hybridization? sp3. For square planar, what is the hybridization? dsp2. This is what we have discussed. Now, in the first case, for NiCl4 2 minus, for NiCl4 2 minus, first, what is the oxidation number of Ni nickel over here, guys? Nickel is considered as X. So X minus 4 equals to minus 2. So X is coming as plus 2. Yes or no? X is coming as plus 2. Now, guys, if you see Ni2 plus, what is the electronic configuration? See, it is 28. 28 means, guys, it's gonna be argon 18, 3d8. I'm not gonna write 4s2 because, guys, 2 electrons are gone. Simple. 3d8. Now 4s0, 4p0, 4d0. Correct. Now the point is chlorine. What kind of ligand is it, guys? It is a weak field ligand. How do I know that? I told you, cyanide, nitrosyl, carbonyl, and polydentate ligand, and ammonia. Only these 5 systems are actually our strong field ligand. Rest all are weak field ligands. So here, as it is weak field, as it is a weak field, that means, guys, would there be any pairing? See, weak field means, in a rough, let's do this. Weak field means the splitting has been less. If the splitting has been less, that means when I put the electron, the 4th electron I'll be putting up here, because, guys, pairing energy is greater than delta O over here. High spin complex, correct? So that means, guys, no such pairing. For weak field ligands, we don't pair up. 1, 2, 3, 4, 5. So 1, 2, 3, 4. Okay, let's not do it in this way. You get confused. 1, 2, 3, 4, 5, 6, 7, 8. 3d8. Then 4s. Then 4p. Now, guys, how many orbitals do I have? I have, how many ligands do I have? I have 4 ligands. So you put 4 ligands, 1, 2, 3, 4. Right? This is your 4s orbital. This is your 4p orbital. So, guys, what is the hybridization coming then? This is Cl minus. This is also Cl minus. This is also Cl minus. This is also Cl minus. Correct? Coordinate covalent bonding. What is the hybridization coming, guys? sp3. That means, what is the shape? Tetrahedral. How many unpaired electrons are there? Right? Now, guys, tetrahedral means this is how NiCl4 looks like. NiCl, Cl, Cl. Remember, they are all coordinate covalent bonded to nickel to the substrate. Okay. Let's solve the NiCN4 wala question now. Let's solve NiCN4 here. NiCN4 2 minus. Okay. When you solve NiCN4 2 minus, what actually happens over here is, let me see first. So here also, guys, you take nickel as X and cyanide is -1 each. So X minus 4 is equals to -2. So X is coming as +2. That means again Ni2 plus. Guys, Ni2 plus, we have just done it a minute ago. It is PD8, 4S0, 4P0, 4D0. Now, as a result, as it is D8, we are going to go like 1, 2, 3, 4, 5. Okay, one thing, guys. Let's not fill it up. What kind of ligand it is, guys? What kind of ligand is this? This is a strong field ligand. Cyanide is a strong field ligand. I haven't yet told you guys why are they strong field, why are they weak field. That comes right after this point. So this is a strong field ligand. So for strong field ligand, what would happen, guys? For strong field ligand, as we have learned, the splitting would be high. The splitting would be high. If the splitting is high, then guys, when I have to put 8 electrons, let's say 1, 2, 3, 4, 5, 6, 7, 8. These were the 8 electrons. How would I put it? 1, 2, 3. Then what should I do? Should I go up or should I pair it up? Guys, here delta O is greater than pairing. That means the splitting energy is more. As a result, we don't make the jump. We go for pairing, correct? So we went for 1, 2, 3, then 4, 5, 6. All filled up. Now, guys, you don't have any other option. You have to go up now because all the systems are filled. So 7, 8. Always remember, the orbitals in similar energies get filled equally first. That's the Pauli's exclusion principle. So, guys, what is the electronic configuration then? First 3 orbitals, you go like 1, 2, 3, 1, 2, 3, 1, 2. Then in EG, you go like 1, 1, 1, 1. This is your ticket. Correct? Okay. 1 second. This is 1, this is 1. Oh, sorry. Let's do one thing one more time here. There's one problem that happened. Okay, go like this, okay? Don't draw it in that way. So as the delta is greater than pairing, that means, guys, we would not make the jump, we would go for pairing, correct? We would not make the jump, we would go for pairing, correct? So 8 electrons, if I go for pairing, how would it look like? 1, 2, 3, 4, 5, 6, 7, 8. There'll be no unpaired electrons, right? They'll be all paired up, correct? So as a result, there'll be a vacant d orbital here, guys, in 3D. Then I have 4s orbital. Then I have 4p orbital. Now 4s orbital, then I have 4p orbital. Now what you have to do is, you start pulling the electrons in. So this is 1 cyanide. This is 2 cyanides. This is 3 cyanide. This is 4 cyanide. So guys, what is the hybridization coming in that case? The hybridization is coming as DsP2. DsP2. That means it's a square planar complex. Guys, see, no need to complicate things over here. Thing is very simple. Whenever you see strong field ligand, pair the systems up, because there the pairing energy is less. Whenever there is a weak field ligand, don't pair them up, because guys, there the octahedral splitting is less, right? It's a very simple thing. So how is NiCN4 gonna look like? Ni square planar, right? So first you make a square, and then you 1, 2, 1 Cn minus, 2 Cn minus, 3 Cn. Okay, let's solve another question now of this type. Let's say they have given you K4 FeCN6. K4 FeCN6. They're gonna ask you the hybridization. They're asking you the hybridization. How would you solve this question? First of all, guys, the hybridization is only for the central metal atom. That I have made it clear to you. So first you find out the primary valency of it. So these ones are +1 each, this is -1 each. So +4 plus x minus 6 is 0. So x is coming as +2. That means, guys, this is iron in +2 oxidation state. Iron is 26. So +2 oxidation state would be argon 18 3d6 only, because 4s2 electrons are gone, right? Now, then 4s would be 0, 4p would be 0, 4d would be 0. Now, guys, cyanide, strong field or weak field? Cyanide, strong field, correct? Strong field. Cyanide being strong field, what would I see, guys? I would see delta O greater than pairing. So, guys, we would do pairing, correct? There would be pairing happening in there, right? So now, let's put these electrons up. So pair them up, guys. The 6 electrons. 1, 2, 3, 4, 5, 6. That's how you're gonna put 6, correct? Then you have 4s. Then you have 4p. Then you have 4d. 3d, 4s, p. Now, guys, if you start putting the electrons in there, then this is the thing. 1 cyanide, 2 cyanide, 3 cyanide, 4 cyanide, 5 cyanide, 6 cyanide. What is the hybridization, guys? T2sp3. What do we call them? Inner orbital complex. They are still octahedral. There is no doubt about it. They would look the same. They would look the same. They would look the same. But, guys, we'll be calling them inner orbital complex. How many unpaired electrons are there? 0 unpaired electrons. Are we getting this, guys? Are we? If you have got this so far, now you try some questions up. Okay, I'm going to give you some questions. Try them up. First question is, guys, NiCO4. Try this question. Then you try K3 FeCN6. You have done potassium ferrocyanide. Now do potassium pericyanide. Then you solve. Okay. NiCO4, K3 FeCN6, CuNH3 whole 6 3+. Try to find out the hybridization, guys, for all these 3 questions and put it in the comment section. Okay, put it in the YouTube comment section. If I see that you are right, I'll be definitely replying you back there. But make sure, if you're watching this video up to this point now, you make sure, guys, you put it in the comment section, solve these 3 questions and try to put it in there. Okay, that is that. Now, guys, this way we can understand the bonding over here so far. Now, that was the entire story about the coordination compounds and the bonding in coordination compounds. Now, guys, if you remember, we started with understanding the octahedral species. What is the, according to crystal field theory, what is octahedral species? When the ligands are approaching along the axis, correct? Now, what is the tetrahedral species? According to crystal field theory, what is the tetrahedral species? Now, see what they say. Now, they're saying like, when a metal is approached, when a metal is approached by the ligands, along the plane, they are called the tetrahedral complex. Guys, this part is not there, not necessary for you, but I'm just telling you, by now you can solve every single hybridization, every single bonding question, correct? But this is just, I'm giving you an insight, okay, an extra information. Like octahedral species are approached by the axis, but the tetrahedral species are approached by the planes. As a result, now what will happen? See, because they are being approached by the planes, as a result, guys, in tetrahedral species, the d orbitals which are along the planes, which means dxy, dyz, dzx, as the ligands are approaching along the planes, now the planar orbital would get destabilized. Earlier, guys, the ligands were approaching by the axis, so the axial orbital got destabilized. Here they are approaching by the plane, so the planar orbital would get destabilized. dxy, dyz, dzx, these are gonna be destabilized now. And who are gonna be stabilized? The rest of the two, dx square, y square, and dz square. The above ones are called T2, the lower ones are called, correct? Now, this particular splitting, guys, this is for tetrahedral complex, so we call it delta T. Octahedral is delta O, this is delta T. The relationship is still going to be the same, guys. Make sure that the total stabilization and the destabilization value has to be the same. They have to compensate each other. So the destabilization value is 0.4 delta T of each of the orbitals, and the stabilization is 0.6 delta T. Make sure, guys, the overall value is same, right? So you can add them up. So there has been a minus sign because it is stabilizing. It is just a second. This is minus 0.6, okay? Because then the two of them would become minus 1.2, and this is also plus 1.2. So overall, change in energy is 0, right? Conservation of energy is being maintained here. So, guys, for octahedral, the splitting is T2G below, EG above. For tetrahedral, it's opposite because the approach of the ligand is opposite. Okay. In octahedral species, as 6 ligands are involved, whereas in tetrahedral only 4 ligands are involved, so delta O is greater than delta T. Guys, very, very logical point. If you have been approached by 6 ligands, then your donation is more, then your repulsion is more, then your separation is more. As a result, octahedral species are always more separated than tetrahedral species. So delta O is always more than delta T. How much more? By how much extent are they more, guys? So delta T can be written as 4 by 9 delta. Delta T can be written as 4 by 9 of delta O. So this is the conversion factor you can see. If you have to convert the delta T to delta O, this is the way you can make it happen. Okay, guys? So that was all about the bonding segment. Now let's go for the last two part of this chapter, guys, which is the color of the coordination compound and the magnetic moment. Guys, the magnetic moment is a very simple thing. What happens in magnetic moment is, when you talk about magnetic moment, you have been seeing that I have been noticing the number of unpaired electrons in every single situation. If you want to find out what is the degree of magnetism in that, all you have to do is, guys, you have to use this formula, root over of n into n plus 2. This is the same formula you have used in coordination, in DNF block for magnetism. So if you put the value of n means number of unpaired electrons, which is 0 over here. So that's why whenever there is no unpaired electrons, because there is no magnetic moment, that's why, guys, these kind of species are also known as diamagnetic. That's why they are also known as diamagnetic. Okay. So similarly, for every single scenario, you can find out the magnetic value. Here also, this is also diamagnetic, guys. Generally, strong field ligands gives you diamagnetic speed. Because if the n is 0, that means the new value is also 0. Bm is the unit of magnetic moment, guys. Okay, Bohr magnetism. Okay. So what is the magnetism in here? We do it. Nu is equals to root over of 2 into 2 plus 2. N is equals to 2 over here, right? So that is coming as, it would be coming, if you just solve this question, it would be coming close to 2.9 or 2.8, something like that. Okay. Bohr magnetism. Right? For this is also diamagnetic. Yeah, that's how you can find out the magnetism. Magnetism is nothing important in it, guys. It's a very simple. Just use the formula and find out the. Let's now talk color of a coordination complex. Color of coordination complex. How do you find out the color of a coordination complex? This is the last topic, guys. Then the molecular orbital diagram is the thing that I'm going to show you how that. Okay, what is the color of coordination complex, guys? See, whenever we are trying to find out what is the color of the coordination complex, that depends on three kinds of electronic transition. That depends on three kinds of electronic transitions. What are they? One is PD transition. Then we have ligand to metal charge transfer. Then we have metal to ligand charge transfer. These are the three. In your syllabus, you have only DD transition. Okay. Now, let's say I have a compound which is Ni, NH3, full 6, 2 plus. And I have another compound which is Ni, Cl, 6, 4 minus. These are the two compounds. What type of colors are they gonna show us? That's the question. Okay. Yeah. So guys, NiNH3 is a strong field ligand and Cl is a weak field, correct? When you have a strong field ligand, you would be having greater splitting. The splitting would be high. Whereas the weak field ligand, for them, the splitting would be low, correct? Now guys, what is showing color? When the electron is transitioning from E2G to EG, that is when you see a color. That is when they absorb the energy, and that is when you see the color. So now guys, for strong field ligand, the delta E or the energy gap is high. If the energy gap is high, that means guys, the lambda absorbed means the wavelength which has been absorbed, that would be low. Why? Because of the Planck's equation, you know, E equals to hc by lambda. So E is inversely proportional to lambda. That means guys, if the energy gap is high, then the lambda would be low. Similarly here, the energy gap is low, energy of the transition is low, so the lambda absorbed. So the absorption energy we are talking about, that is high. If lambda absorbed is low, that means in which region, guys? Red is a high wavelength, blue is a low wavelength, right? So the absorbed light, now this is the important part. Color absorbed, this would be in the blue region, because guys, the lambda absorbed is low, so you'd be able to see the color absorbed would be in the blue region. But the color that we see, that is not the absorbed color, we see the transmitted color. So the color transmitted would be opposite, would be in the red region. See guys, there is something called color wheel. According to the color wheel, whatever color you absorb, the color you transmit would be its opposite color, opposite range color. Example, this is the example I give all the time. If you see the green leaves are green, in the color wheel, guys, green is a color who is actually opposite color is red. So actually, you absorb the leaves, the magnesium of the chlorophyll, they absorb the red color from the sunlight. Sunlight is white, it has all the 7 colors. It absorbs the red color from the sunlight and it shows us green. The transmitted color is green. That's the thing. If you can see an orange point over here, guys, orange is a high wavelength. Red, orange, yellow, these are high wavelength. So it is absorbing the color of a low wave. That's why it's transmitting the color of a high wave. Similarly, here, what am I gonna say? The color absorbed would be in the red region, but the color transmitted would be in the blue region. It's impossible for you to understand, guys, what would be the color. You can never know. They have to tell you that. But you can tell them, like, how can they show this kind of coloration? They would give you the color, but you have to explain that why. So whenever you have a strong field ligand, guys, the energy gap is more, lambda would be less, lambda of absorption would be less. So if the lambda of absorption is less, lambda of transmission would be more. So as a result, the color would be in the red region. Okay, that's how we go for this one. Clear, everyone? So this was the color of the coordination compounds. Okay. Now, just one second. Yeah. Now what you're going to do is, okay. Now guys, solve this question and write it in the comment section. If I have a question for a molecule which is APCH6 4 minus, what would be its color? Would I see a color in the high wavelength region, or let's say there are two options that I'm giving you, okay? One is the color of this has been found to be yellow. Yellow means high wavelength, guys, okay? Or it is found to be violet. Violet means low wavelength. So tell me which one would be the right answer. If it's APCH6 4 minus, would it show yellow wavelength or would it show violet? Which color would I see? So write it down in the comment section of the under this video, okay? So that was your color of the coordination compounds, also covered up in this one. Now guys, we would see what kind of things can they ask from the carbonyl molecular orbital diagram. See guys, I've been telling you from day one that this carbonyl MO is something which is a very, very important part of our discussion. What happens in carbonyl systems or cyanide system or all the systems that we have pointed out as strong field ligand? What happens with them? Why are they strong field ligand? Why are they considered as a strong field ligand? That's the point of discussion right now. So guys, I have told you this, that cyanide, carbonyl, nitrosyl, these are all strong field ligands, and they are strong field, guys, because of the condition called synergistic effect. What is the synergistic effect? See, there are many types of ligands out there in coordination. One is sigma donor ligand. Then we have sigma donor pi acceptor ligand. Then we have sigma donor pi donor ligand. In our regular classes, guys, I'm going to discuss about these things into details. Right now, all I'm going to tell you is, all you have seen so far is a sigma donor ligand. Like all the ligands that you have seen, they all have made single bond so far, isn't it? None of them has made double bond. But that's the point for carbonyl system, guys. Carbonyl, cyanide, nitrosyl, they make double bond. They make multiple bonds in there. Now for carbonyl, nitrosyl and cyanide, they come under sigma donor pi acceptor ligand. Now why are they like that? Okay. First, let's focus in this molecular orbital diagram. Have a look. Guys, we know that when we are talking about carbonyl systems, you know, C double bond O, and the O makes a dative bond here from the left hand side. So you get this kind of compound. This is carbonyl. This is the bonding of carbon monoxide. So guys, carbon monoxide is here in the carbon over here is an sp hybridized system. When you have an sp hybridization, that means you know that there is one s orbital and 3 p orbitals in reality, right? In sp hybridization, you take an s orbital and you take a p orbital. Right? 2 p orbitals are still left in that situation, yes or no? So in sp hybridization, we have 2 sp hybridized orbitals, s and p, and then 2 p or p orbitals. That's what they have drawn here. 2 sp hybridized orbitals, this and this, and 2 p or p orbitals. Clear so far? Okay. Now when you're seeing that, when they're talking about carbon, this was your PO, carbonyl system. Okay. sp hybridization and p or p orbital, like that. Now when you see the molecular orbital diagram over here, you don't have to look into this into details, guys. If you're somebody who is pursuing only for your school examinations, you don't have to know about this in detail. I'm just showing you, giving you an overview of this topic right now. Okay. Now here, if you notice, what is happening here? There is a molecular orbital diagram being drawn. Now this is first time you are seeing, because you have never seen any heteronuclear molecular orbital diagram. All you have seen is homonuclear molecular diagram. Means you have seen for H2, you have seen for N2, you have seen for O2, similar atoms. First time you are looking at CO, two different elements, atoms. As a result, guys, there is something that you are supposed to notice. Do you see that the carbons orbital are drawn here and the oxygen's orbitals are drawn here? They're not in the same energy range. Why is that? Because, guys, the electronegativity of oxygen is greater than the electronegativity of carbon. As a result, the oxygen's orbital are more stabilized than carbon. As a result, guys, that they are a little down below. So this picture that I'm showing you now, this is coming from a research article. So this is completely authentic picture, guys. Okay. Now, so because of that, the molecular orbital diagram for this system is a little bit complicated and beyond your understanding, those who are actually preparing for the board examination. And I would not suggest you to do that as well. In our advanced classes, guys, I would show you this entire molecular orbital diagram in detail, right? Right now, just focus on the point of sigma donor pi acceptor bonds. I told you that the carbonyls are sigma donor pi acceptor system, correct? What do I mean by that? That means if I start putting the electrons in over here, guys, let me see. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons I have to put, right? Let's start putting in them. 1, 2, 3, 4, 5, 6, 7, 8. Right? Guys, see, the orbital which is occupied, the last orbital which is occupied, that is called HOMO. HOMO stands for highest occupied molecular orbital. And the orbital right above it, it's called LUMO, lowest unoccupied molecular orbital. Highest occupied molecular orbital, that is HOMO, and LUMO is lowest unoccupied molecular orbital. Carbonyl system shows a very special characteristics. This is the electron that they donate to the metal to make the sigma bond. And the metal, guys, it's a synergistic effect. Synergistic effect means, see, I need you for to learn something new, right? Every teacher, like this is something that I believe, guys, that person is a perfect teacher who learns from the students as well. So when I come to take your sessions, guys, I learn a lot of things from you, and you also learn a few things or two from me as well, right? This is called synergistic relationship. So we both need each other. That's the kind of relationship we have. Right? Same thing happens over here. The carbonyl system donates the lone pair of electrons to the metal. Metals which orbital? D orbital, correct? And then the metal now donates electron back to carbonyl in its LUMO. So guys, carbonyl gives its lone pair from the HOMO and it takes the electron back from the metal in the LUMO. It does take back, guys. That's something that you're hearing for the first time. That's why, guys, we say sigma donor means it donates electron to make sigma bond, but it makes a pi bond as well by accepting the electron. By accepting the electrons, it is making a pi bond as well. So, guys, metal in carbonyl has a double bond character. It donates from HOMO, it accepts in LUMO, right? Now, let me show you how does it look like because of that. So, the diagram I have shown you is down below here, guys. Okay, you'll be able to understand this diagram if I draw it for you. See, this is the metal. This is the carbonyl. Guys, I told you that in carbon there is a lone pair. Okay, carbon there is a lone pair. Where is it actually? It is not in, you cannot say it is carbon's lone pair, guys. You cannot say it is oxygen's lone pair. You are grown up now. You are referring to the molecular orbital diagram. So you're going to say it is a lone pair of carbonyl HOMO molecular orbital, highest occupied molecular orbital. That HOMO electron goes to the metal d orbital. And the metal also donates electron back to the LUMO of the carbonyl complex. So that's why you can see that pi acceptor ligand. This is pi donor ligand they're talking about. This is out of his syllabus, pi acceptor. In pi acceptor ligand, what happens is, see, they are accepting electron. Sigma donor, pi acceptor. This is a sigma bond they are gonna make. This is the pi bond they are gonna make. That's called sigma donor, pi acceptor. That's why, guys. Last statement. Because of synergism, metal carbonyl complex are shown in double bond character. Double bond character. That's it, guys. Now, because of this reason, guys, carbonyl systems are strongly ligand. Because other ligands are connecting, but carbonyl systems are connecting with multiple bonds. So that's why they are strongly ligand. So far, guys, we have discussed about the entire coordination compounds now. There is nothing much to talk about here, right? I would suggest you now to answer the question whichever I have asked you down below. Maybe I'll be making one more session, guys, on carbonyl complexes just to solve some questions, right? That depends on the on your demand on it, guys. So if you really want me to solve the NCERT back exercise questions or some PYQs from the JEE mains level, it's what I need is, guys, I need your comments. You have to write it down in the YouTube portal, YouTube comment section. If you need it, we'll be making more videos like this, right? And guys, one more thing. This is something I need you to know here. This series that I have made so far for this coordination chemistry, this is just the first series. Right now, right after this, I'm gonna launch the hydrocarbon series, right? Because organic chemistry, you need the hydrocarbons chapter, right? So that is gonna be launched right after this, guys. Okay, so I believe that you have watched the entire videos, all the 3 videos. Now the very next step is, guys, read the entire thing, whatever I taught you from the NCERT, line by line. See that whether you can understand the things or not, right? And then you try to solve the questions the way I told you. Again, I'm gonna tell you, I'm gonna repeat this thing. So if you want me to solve some questions from the NCERT as well, put it in the comment below. I'm definitely gonna make another video. Guys, we have to work really hard in order to make these kind of videos and all. You can understand how much time consuming it is, and we have to take this reference and this all these things from different books so that we can give you the authentic informations and stuff, right? So I would definitely appreciate if you leave a like and do subscribe to our channel as well. That would be it for today, guys. Bye everyone. All the best for your exams. Bye, guys.